last type of reaction that we're going to be looking at is called a precipitation reaction, and this is actually just a double replacement reaction. And we'll look at one other type of double replacement reaction, which is acid-base reactions. So a precipitate in a precipitation reaction is an insoluble solid that is formed by the reaction. Okay, so let's see how that insoluble solid is actually formed. So we're going to be using our solubility rules again, just like what we did in the single replacement section, just as extra review for you. So in this example, you've got two different compounds, and they're going to form two new compounds. Specifically, I'm first going to write out the molecular equation to help you to see what's going on. So I've got copper with a 2+ charge. Chlorine has a -1 charge. So the formula for this would be CuCl2. And it's going to react with sodium sulfide. Well, sodium has a +1 charge. Sulfur has a -2 charge, so it would be Na2S. And so what happens in a double replacement reaction is that you just exchange partners. So Cu is going to form, copper is going to form a compound with sulfur, and sodium with chlorine. I call it innies and outies. So copper has a 2+ charge, sulfur has a 2- charge, so I'm already crossed my charges. Na has a +1 charge, Cl has a -1 charge, so this would just be NaCl. And the last thing you need to do is balance. I'm going to put a 2 there, and now I'm balanced. The next thing that you need to do is you need to break apart into ions anything that is soluble. So if you look at chlorides, all chlorides at your solubility guideline, it tells you that they are soluble except for silver, mercury, or lead. Well, this is not silver, mercury, or lead, so I know this is going to be soluble. So it's going to be copper with a 2+ charge. Then I'm going to have 2 chloride ions, so 2 Cl- plus 2 sodium ions, and I know that's soluble because sulfide ions are insoluble except when they're with alkali metals, which is all group 1 metals. So this is going to be soluble, plus sulfur with a 2- charge. Okay. Then I look at copper sulfide. Well, all sulfides are insoluble, meaning they're going to stay together unless it's with ammonium, alkali metals, calcium, strontium, or barium. So this is going to stay together, so Cus. And then sodium chloride is soluble because you've got an alkali metal, which is always going to be soluble, so Na+, and 2 chloride ions. And then what you need to do, just like what we did before, anything that stays identical, you are going to get rid of. So notice copper does not stay identical. It actually forms a compound with sulfide, but the chlorine stay the same, the sodium stay the same, and so what I'm left with for my net ionic equation is copper plus sulfide ion, which produces copper sulfide. So keep in mind that your net ionic equation, what it does is it shows you the ions that are involved directly in the reaction. Okay? The ions that are not directly involved, the ones that you cancel out, those are called your spectator ions. Because while they're dissolved in the solution, they don't actually play a direct role in the reaction itself. So I'm going to explain how to name acids, but before I explain that, we have to be able to identify them. So just a common thing for you to know, if you have a molecule that begins with H, that becomes with hydrogen, it tends to be an acid. Now, there are obviously going to be exceptions, so for example, water and hydrogen peroxide. But for the most part, if you see a compound that starts with hydrogen, it's probably going to be an acid. So that's an easy way to identify them. Now, there are two different main types of acids, those that just have an anion and those that have a polyatomic ion. So let's talk about ones that just have an anion. So acids that contain only an anion, which remember is going to have that IDE ending, what you do is you're going to change the "ide" to "ic, and then you're going to put the prefix hydro. So for example, if you have HCl, that would be hydrochloric acid, or hydrobromic acid, or hydroiodic acid, or hydrofluoric acid. If, however, you have an acid that has a polyatomic ion, so for example, it has an ATE ending, that ATE ending is going to be changed to an IC ending, just like what we did before. The only difference is you don't put the hydro in front. So for example, if you have an acid with sulfate, it would be sulfuric acid. Or for example, if you had one with NO3, which is nitrate, it would become nitric acid. So no hydro, just the ic ending. If your polyatomic ion is an ite, so for example, HNO2, NO2 is nitrite. That ite becomes us, so it would become nitrous acid or sulfurous acid. A way that my students, a trick that they use in order to remember this is they say that if there are 8 people at a gathering, that's too many, so that's ic. But if it's just us, it is all right, or ite. So ite goes with us, 8 goes with ic. So let's try an example. So here are 3 right here. If you notice HBr, you just have the anion, so you're going to need your hydro prefix. So it's going to be hydrobromic acid. For HNO3, that is a polyatomic ion, that's nitrate. So it's going to be, you're going to replace the 8 with ic, so it's just going to be nitric acid. So no hydro needed because that's a polyatomic ion. For HNO2, that is an ite ending, so it's going to be nitrous acid. The next thing we need to be able to do is identify strong versus weak acids and strong versus weak bases, and you'll see why in just a second. So your strong acids, these you're going to have to memorize, so you can create some sort of mnemonic to memorize them, but here they are. They're HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid. So that ClO4 is perchlorate, so that would be perchloric acid, nitric acid, sulfuric acid, and that's it. So those are those 6. So you got to somehow memorize those because, as you'll see, strong acids completely dissociate. So when we are writing out a double replacement reaction, if you have a strong acid or a strong base, they're going to break apart, while weak acids and weak bases do not. So it actually really does matter that you memorize these. And we're going to look at this pretty intensely next year. So learning them now over the summer is going to be very helpful. Okay, so for strong bases, remember a base, just from review from first year chemistry, bases end in OH. So your strong bases are going to be your group 1 bases, so anyone in your group, any of the elements in your group 1 with OH, or calcium, strontium, or barium. Okay, those with hydroxide, those are your strong bases. Okay? So those are a little bit easier to memorize than your strong acids, but take the time and memorize them now so you don't have to over the school year. All right, so I'm going to write out the double replacement reaction between potassium hydroxide and hydrofluoric acid. Now this is just like the precipitation reactions that we looked at just a little bit ago. However, you're going to see that there are a couple of differences here. So first of all, I'm going to write out my reaction. So potassium hydroxide is KOH. That reacts with hydrofluoric acid, which is HF, and it produces KF. Remember, you do innies and outies, so K goes with F, and water, because when you have H and OH come together, no matter how many hydroxides or how many hydrogens you have, it's going to produce water. So now I need to break up anything that is soluble. Now, we're not going to use that term here because instead we're going to talk about them being able to dissociate. So KOH is a strong base, which means it is going to completely dissociate, meaning it's going to break up into its ions. So this would become K plus and OH minus. HF is a weak acid, so it's not going to break up, so it's going to stay as HF. Then KF is, we're going to now look at our solubility rules. Remember, from your solubility rules, group 1 metals are always soluble. So KF is going to break up, so it's going to be K plus and F minus, and water does not break up. Okay, so anything that's the same on both sides, you're going to eliminate. So the only thing that's the same is your potassium ions. So you're going to be left with hydroxide reacting with hydrofluoric acid to produce F minus and H2O. All right, so this is extremely similar to your precipitation reactions. The only difference is, well, first, you're making water, and secondly, you're looking at strong bases and strong acids. Those you dissociate, while weak acids and weak bases you do not.